So here's a problem. Here's our first problem where we need to apply dimensional analysis. And the problem says, let me see if I can move this. Okay, show that the expression v equals v0 plus at is dimensionally correct. So what does that mean? That means we have a velocity. This is equal to some initial velocity at an initial time, plus acceleration times time. So we need to show that the dimensions of the left-hand side of the equation are the same as the dimensions of the right-hand side of the equation. Then it's possible that this equation is correct. It doesn't tell you that for sure the equation is correct, but if the two dimensions on the left and the right-hand side are not matching, then certainly the expression cannot be correct, the equation cannot be correct. So dimensional analysis reveals to you when an equation cannot be possible. And it also reveals to you when an equation can be possible, but it does not tell you that this expression or this equation is definitely correct. So for example, there might be a factor of 2 missing somewhere. For example, it could be that v equals 2v0 plus at. And you would never know because the 2 does not show up and doesn't make a difference in dimensional analysis. Okay, so what dimensional analysis can do for you is to tell you if an equation is not correct and not possible. And also it can tell you if an equation is possible, but it cannot tell you that it is definitely correct. Okay, so we are mostly checking for incorrectness. So in this case, what we can do is we can, let me use a pen. Let's look at the left-hand side here. This is velocity, right? V. So velocity is distance upon time, right? Just like speed. Speed is distance upon time. So the unit for distance is L, and the unit for time is T, L over T. This is how we write the dimensions for velocity. Okay, so when we write the dimensions, we put them in square brackets. These square brackets are telling you that you are now writing dimensions. The dimension for v0, since this is also a velocity, so these are exactly the same as v. So v0 on the right-hand side also has the same dimensions. So these two terms have the same dimensions. Let's look at this third term, at. So a is acceleration. That's the rate of change of velocity. Here's velocity. You need to divide this by time, so you get L over t squared. So this portion here is my acceleration. Okay, that was really badly done. And acceleration times time, that's just t. So these terms can be algebraically cut. So just like you had before, you can actually cancel this term with this squared term, and you get L over t as the remaining term. So what do we have now? We have v as L over t equals v0, which is L over t, plus L over t. So all the dimensions are the same, all of them are L over t, hence we say this expression is dimensionally correct.